Hi, everyone, and welcome to today's webinar on motors and drives, brought to you by Plant Services and Timken Power Systems. I'm Tom Wilk, the Chief Editor of Plant Services. Thank you for joining us today. This webinar is sponsored by Timken Power Systems. The Timken company designs a growing portfolio of engineered bearings and power transmission products to continuously improve the reliability and efficiency of global machinery and equipment. And before I introduce today's speaker, there's a few housekeeping issues I'd like to review with you. On your screen, you should see several primary sections. The upper left or audio control section allows you to adjust the volume of the presentation. Just hover over that section with your cursor until you see the audio controls and then adjust it to your preference. To the right, in the largest section, is where today's presentation slides will be displayed. Under that slide window, you'll see a chat section where you can chat live with fellow audience members. At the left of the slide window is the Ask a Question box, and this is where you can type in questions for today's presenter at any time during today's webinar. If you're here on live day, we'll get to as many of those questions during the live Q&A session following the main presentation. And if you're listening on demand, you can also feel free to type questions in that box, and those questions get routed right to the presenter, who will contact you one-on-one via email to answer your question. If I can also refer you to the handout section. This section contains a link to the full set of today's speaker slides, as well as an ebook on how to supply and service the drivetrain, and a link to a video on Timken Industrial Drivetrain Repair Services. For those of you listening on demand, there's also several links to further video content from Timken Power Systems. Finally, at the edge side of your screen, you should see icons for additional features. By hovering over each icon, information about it will be displayed. If you have any technical problems, please type your question or concern into the Ask a Question box, and one of our technical engineers will assist you directly. If you need a better view of any section, especially the main slide presentation window, you can enlarge these sections by clicking on the box in the top right corner of the section next to the X. If you accidentally close out any sections, you can get them back by clicking the Restore icon. It's the icon in the shape of an arrow in a circle. Finally, this webinar will be archived, and we encourage you to direct coworkers to the recorded presentation. And after today's presentation, we'll ask you to complete a very brief survey to provide some feedback that we can use to improve future webinars. And now I'd like to welcome Henk de Swart, who will deliver today's presentation on Can I Maintain and Repair My High Efficiency Motor? Henk has served as the Chief Electrical Engineer at Timken Power Systems since 2019 and currently leads the engineering team at Timken's 4 electric motor repair workshops, where he conducts failure investigations and root cause analysis on high-profile cases. His extensive practical experience has allowed him to author 5 published IEEE papers, invent 2 registered U.S. patents, design many unique motors, and complete technical audits on more than 30 of the major service shops in the United States. Welcome, Henk, and thanks for presenting with us today.
Good afternoon. Thank you very much, and thank you for all the attendees that's listening to this presentation about high-efficiency electric motors. Start right off with a little bit of content. I'm going to start off with an introduction, defining efficiency in electric motors. How is it measured? How is it defined and calculated? And we're looking at some different losses in electric motors. And the point of that study is to show that in each portion of the machine's losses, we can look at these and say, how are these affected by a repair? For this, we're going to look at 2 different types of repair processes, which I will explain. And we'll look at the changes in the losses due to one of these repair options. And then we're going to do 2 case studies. One is a nice big, a 43,247 horsepower machine that had a failure. It's the actual study of an actual machine that failure. We're going to look at what happens to the losses, or what could potentially happen to these losses during a repair. And then we'll end of the case study with what really happened. In this case study, what really happened. And then in case study 2, I'm going to expand a little bit more on what about the efficiency of a machine? What can we do potentially to improve the efficiency of an existing machine? Then I'm going to do a short conclusion, and then I'll have some additional resources available. As an introduction, The focus on energy costs for many decades has resulted in a large installed base of thousands and thousands of high-efficiency medium voltage motors across the United States, as well as the rest of the world, although high-efficiency motors are not defined for medium voltage motors. As we know, for low-voltage motors, IEEE, IEC, and NEMA has got standards that define IEC1 and IE2, 3, 4 different standards for high-efficiency motors. And we're not going to go into that discussion today, but just to know, for the most part, large motors have been designed with high efficiency in mind because the energy cost of running each of these machines is significant. But unfortunately, machines fail. The question is, when I have this beautiful high efficiency motor, when it fails, what do I do? Can I repair it and maintain the efficiency, or should I just replace it? On the right-hand side, you'll see a beautiful specimen. It's actually an old Westinghouse motor, probably in a range of about 50 years old, a 3,000 horsepower nuclear certified motor that was rebound by one of our companies, Electric in Connecticut. Now, for these beautiful machines, some of them 50 years old, what can I do? Should I fix them every time? This is what we're going to look at today. From a design engineer's perspective, like myself, the question is almost, how could it not be possible to repair this high efficiency motor? I'd like to show you higher and give you a little bit of an insight of what these machines, their losses are about, and what can we do to make sure that we do repair it correctly. So this this paper will focus mostly on medium and high voltage motors and generators. The same principle is true for all the machines. If we define an electric motor, it's often misunderstood that the losses in an electric motor is so large. It actually is not. Electric motors and generators are some of the most efficient machines in the market. If you compare mechanical equipment, fans, pumps, compressors, by far electric motors exceed the efficiency by 20, 30, even 40%. So let's look at what is the definition of efficiency. Now, a textbook definition of efficiency is the output divided by the input, which of course would give us a percentage which would be less than 100%. Now, if we look at the input power, we could say the input electrical power is the mechanical power, the losses. And then we can rework our efficiency calculation to see that our efficiency is the output power divided by the output power plus the losses. So we can see in this equation very easily, as the losses increase, the efficiency will decrease. And that's why we're going to look now at the specific losses. Now, the losses in an electric motor can be defined as the iron losses, the stator conductor losses, the rotor conductor losses, friction and windage losses, and stray load losses. And on the right-hand side, you'll see the picture of it's literally dumping money down the toilet. When the losses goes high or higher, it's money wasted. The losses get translated into mostly, which is also a problem because often in a plant we need to get rid of. We will explain each of these losses and how they are influenced by the repair when we looked at two specific repair conditions, which is quite common. The one is the routine overhaul. For instance, every 4 years, 5, 6, 7, 8 years, a company would take a motor out of the plant. They would send it into a electric motor repair shop. They say, give it a spit and polish. What the repair company would do is typically, if it's anti-friction bearings, being ball and roller, they would replace the bearings and they will wash the machine, the stator, the rotor, and clean it and dry it out, reassemble everything with the new bearings, and give it a test run, and then send it back. That's what we consider a routine overhaul, which is normally done every 4+ years. However, when the machine fails, you very likely will have a stator rewind. Now, there's been a lot of studies by IEEE and others that show when machine failures occur. I don't want to delve too much into that, but in order to quantify the losses that we're going to look at, normally, in general, when you look at large machines, probably up to about 5,000 horsepower, if you go to a very harsh environment like mining environments, you typically find that these machines fail around a Stator rewind somewhere around 8 years. If you look at very, very sophisticated environments like petrochemical, these machines would typically last 15 to 20 years before they require a Stator rewind. So I'll use this again these times when I explain when these failures occur and the losses. Let's first look at the big one, the iron losses. On the left-hand side, you will see Stator core. There was Stator winding failure, and you can see that the laminations, the top of the laminations is burned very, very badly. Obviously, that becomes a mechanical problem in that you can't get the Stator coil into the slot, but also the core losses of that core was severely increased, and the core was found not to be suitable to be used. So the replacement motor will set back the customer with a delivery lead time of 6 months, perhaps even longer. So what we did at was the electric workshop in Denver is we replaced the core with a brand new core that you can see at the bottom that restored the machine basically to new. The copper the iron losses went down because it's a brand new core, and we had a machine that could work again. Now, looking at the iron losses, they are dependent on the flux density in the core and the material properties. Flux density is dependent on the winding design and the core area. Now, if we look at our repair type 1, the routine overall, it's easy to see that the routine overall, the winding configuration, the core area, the core properties, none of these change, and thus the core losses should not change. However, in the second case, where we do a Stator rewind, we know the core area did not change. We know the winding design should not change. But the core material, what happens with that when you burn it out? And we will look at that specifically. Now let's take for this type 2 repair where we do Stator rewind, let's look at this core material. Now the burnout process is absolutely critical in maintaining the low core losses. The lamination plates, which is the silicon steel plates, are insulated electrically from each other. And that reduces the core losses. That's why it's called laminations. But an incorrect burnout process could greatly increase the core losses by damaging this interlaminar insulation. Unfortunately, we occasionally see the case of the inferior steel. We just recently had it surprisingly on a 3,000 horsepower machine that after the burnout, even though we controlled the temperature, we made sure that there was no thermal runaway of the machine. Afterwards, when we tested the laminations, we found that the lamination core was severely damaged. The core losses increased tremendously. Investigating a little bit deeper, we found that the company that manufactured these things actually make them throw away motors. Every time you burn it out, you cannot pay the machine anymore. You cannot rewind it because the core losses increases so much. We don't see this often, but be aware it does happen occasionally. And at that stage, the only option left is to replace the core. Now, looking at the iron losses, we know that these iron losses can be kept low during the rewind process, while you have the correct material, and that we do the burnout process correctly. There's been lots of studies done by ESA on how to maintain the core burnout process in order to maintain the efficiency of the machine. Now, it is key to monitor the core losses by testing the core before and after the burnout. But iron losses might still increase if we burn it out multiple times. So what we're going to do is, for the study, is we're going to look at 3 or 4 types of burnout. The first we will call a good burnout process, where the core losses actually will only increase after 3 burnout cycles by 15%. This is not an unreasonable result. We've seen this. You will see at the bottom, there's a table where we see of the first burnout, the core losses actually decreased by 5%. This we've seen on a fairly regular basis. And the reason for this is that during the lamination punching process, the stresses that build up due to the cuts of the lamination of the punching. And basically over time and the burnout process, actually, it's almost like these stresses in these areas gets reduced. Annealed perhaps, although it's not high enough temperature to anneal the steel. We can see often that the losses will decrease after the first burnout. And let's say the losses then increase 205% after the second burnout, 115% after the third burnout. Now we remember back to, for a very harsh environment like a coal mining industry, each rewind is typically 8 years. So 3 rewinds means that is 24 years in the life of the machine, which in most plants is a very significant portion of the life of the plant itself. Let's look at the average burnout process where we will take that after 3 rewinds, that the core losses actually increase by 50% over these 3 rewinds. Then we look at a bad burnout process where the core losses tripled. Now that's insane. 3 times the amount of core losses after 3 burnouts. And then a really bad process, which hopefully we will never see, is where the core losses actually increase ninefold. And we'll take these losses and plug them into the designs of these machines and see what happens. What is the influence on the machine performance? Now looking at the next losses, we look at the stator conductor losses, stator copper losses as is commonly known too. They're dependent on the stator current, and thus they are load dependent. Typically you'll hear of I squared R losses. Now looking back again at our type 1 repair, where I just do a bearing replacement and cleaning of the winding, it's easy to see that the stator conductor losses is not going to change at all. During the rewind, they should also not change because the resistance should be the same. In fact, on some old designs, we sometimes see the potential to actually improve on the machine design by increasing the conductor size, because the modern technology of insulation is so much more advanced to the original machine that was manufactured like 50 years ago, that sometimes we can actually improve on the copper losses. On the right, you'll see a nice 34.5 MVA, 13.8 kV generator stator winding rewind by Smith Services. Now let's look at the rotor conductor losses. Similar to the stator, the conductor losses are dependent on the I squared R, or the resistance and the current, so they are load dependent. Here as well, in case study 2, I'll show you some of the interesting work that we've done, taking an old machine design and see how we can improve it. Now this is different from the stator because in induction rotor, in general, the rotor bars are not insulated. So it's not like I can use better insulation and then put in more copper. But there may be opportunities to actually put in a different material. I've done a couple of interesting case studies on like 400-500 horsepower machines where we took a aluminum die-cast rotor and we replaced it with a copper bar rotor and increased the performance of the machine really, really significantly. You can look at that at some of my reference material at the end. Now, if we look at the repair types, repair type 1, we do overall of the machine, obviously. Rotor conductor losses are not going to change. And repair type 2 is stator rewind, they're also not going to change because we didn't do anything to the rotor. Obviously, there are some other cases with different failures. If you have a bearing that failed and the rotor goes into the stator and you have a core rub, there obviously you need to look at other things as well, which is outside the scope of this presentation, but I'm happy to discuss at a later stage with you. We're going to look at the 2 last losses, the friction and windage losses and the stray load losses. Friction and windage losses is due to airflow and losses in the bearing. Again, it's easy that these losses will not be influenced by either of the repairs because they would not be changed, the windage on the machine or the bearing losses. On the left-hand side, you see horsepower rotor repaired by Smith Services. Preload losses is due to the stray flux and incomplete coupling of the flux in the rotating air gap and surface losses. None of these are going to change significantly during the repair because we're not going to change the core designs. Occasionally, there are times that a failure of a machine lends us the opportunity to do a core replacement like the one seen earlier, and then let's say we might look at go to the customer and say, you know what, this was based on an old design. We can actually change the machine to improve the losses. More of that in case study number 2. Now let's look at our first case study, the big machine, 43,247 horsepower machine failure. On the left-hand side, you will see the actual machine. It's a big boy. Those two men are standing next to it, and they reach just over the center height of the machine. Now, was that this machine? Beautiful specimen. Unfortunately, it's 10 years old, and it suffered 3 failures already, which is quite surprising for such a large machine. Typically, this class of machine, you would look at first stator winding failure after maybe 30 or 40 years. Fortunately, what happened in the history of this machine is they had a defect on the internal cooling fan of the machine, and it failed twice. The customer had the fan replaced successfully. Unfortunately, there was some debris left inside the machine. So what happened was that some of this debris was flung with the fan into the air circuit, and it hit the stator coil. I've only showed you one coil on the right-hand side with, you can see the point of failure where it actually pierced the insulation. Several of the other coils had similar, this was just the point of failure. Fortunately for the customer, their protection circuit was really good, and even though you had to flash the arc, to the stator core, there was no significant damage on the core. You can see a little bit of arcing, but no damage, not a burnt hole, which was really good. But it's unusual for this machine to have failed so early in its life. But again, it's just because of the past mechanical failures there. So let's look at this machine and it's the influences of the losses during this repair. There you can see on the left-hand side, it's a beautiful machine. You can stand in the inside of the stator core and touch the tops of the core when you're reaching out just a little bit. Now, what do we see in this machine? If we look at the losses, we can see that the losses will only really be concerned of when we do a rewind, which we had to do in this case. Now, what we did on this machine, we burnt out the stator winding under controlled process. We monitored the losses before the burnout as well as after the burnout. Let's look at what the performance of this machine could have been if we look at those 4 scenarios of the burnout process. First one is, let's say a good burnout process. We've said that if the losses decrease 5% after the first burnout, increase 5% above the original for the second burnout, and then 15% after the third burnout. Now we can look at the table. We'll see there's the output power. I guess the output power the same, assuming that the plant will remain at the same output power. Of course, I used the unit of measure of kilowatt because we're looking at the losses and the calculation of the efficiencies. So we'll see that the iron losses, as the original was 172 kilowatt, it decreased after the first burnout, 164. Second burnout, it increased to 181, which is quite a lot. I mean, that's 9 kilowatt. Think of 3 stove plates. That's the amount of heat that it's generating. And then after third burnout, that's 198. You can see that the stator copper losses change slightly. And this is because as the losses increase, means the input power increase. And what happens when the input power increase? You will see that the stator current increase and the rotor current will also increase. That's why you'll see a slight small variance on the stator and rotor copper losses. It's not because of the repair, it's as a result of the change in the iron losses. Then we'll see the friction and windage losses, Preload losses stay the same, and the total losses is obviously the total of this. We can calculate the input power, we take output power divided by input power, and we will see that the efficiency of the machine, there is a slight change in the efficiency of the even after 3 burnouts, which in this class of machine, it should have been in the region of 100 years life. Obviously, with this first failure, we know why this occurred, but it should have been in a region of about 100 years. You can see the efficiency only changed ever so slightly, 0.07% after 3 burnouts. If this was a, let's say a 2,000 horsepower in machine in a mining environment, very harsh, very dirty, maybe aggregate, this might still be only 24 years in the machine's life, which is a really good time for it. Now, one other thing that's quite important is the stator temperature rise. Now, why this is important is the stator temperature rise it forms the chemical damage or aging of the stator insulation. And the higher the temperature, the quicker the insulation ages. Now, there's the Arrhenius curve used by many that would say that with every 10 degrees increase in temperature, the life halves. As you can see, between original machine and rewind number 3, the change is ever so slight. You won't even see it. And even when we look at the energy cost-wise, it's very, very small. You can see in this case, 3 rewinds is no problem at all. That's the good process. Let's look at the average process. Now again, the average process, we said that the losses would increase from the original value to increase by 50% after 3 rewinds. You can see where the iron losses increased from 172 kilowatt to 259 kilowatt. That's a really significant increase in losses. Amazingly enough, because the iron losses is only a small component of the losses of the machine, you will see that the efficiency only decreased from 98.41 to 98.15, and the temperature rise only increased by 2.9 Kelvin, which is surprising indeed, with considering that the losses increased by 50. And it would be a really difficult economic justification even to say, let's replace this machine. Even though the losses increased 50%, the economic impact, the impact on the life of the machine is really small compared to what the cost of a replacement machine would be. That's an average process. Now let's look at the bad process, the bad boy. We'll say after the first burnout, it increased 50%. Second burnout with 225, and our third burnout 300%. We'll see that the iron losses increased from 172 to 500 kilowatt. That is a decent size Corvette engine, if you ask me. Now we'll see that the stator and rotor copper losses has increased. That's because of the increase current. Preload losses and friction and windage stays the same, but we'll see the efficiency, surprisingly so, have only decreased by 1%. Now, 1% on such a big machine is a lot of money, but there's been a lot of studies that shown that a voltage imbalance on your line between your 3 phases can easily cause a 1% drop in efficiency of electric motor. So it's a lot, but also not. If we look at that data temperature rise, you'll see 87 and 92 Kelvin. So after 3 rewinds, I halved my insulation life. So a machine that would have lost, in theory, 30 years of insulation life, now I've killed that insulation life to only 15 years. And now definitely one would need to do something about this. It would not make sense to keep the machine as is, because obviously you've destroyed a significant portion of the life of the machine. Now let's look at the worst case scenario. It's very bad rewind. And okay, this is bad. This is a really a bad situation. We would never send a machine like this in the field. We can see, losses increased from 170 to 1.4 megawatts. Yeah, that's a lot. But I wanted to show you, even with the increase from 100% to 900%, we'll see Stator copper losses increase significantly, rotor copper losses increase. My total losses increase dramatically. My efficiency dropped by almost 4 percentage points. Now I can see the temperature rise is going to kill that machine. After one rewind, I've halved the insulation life. Another rewind, I've halved it again. And the third rewind, it's a quarter of it. So you're probably now looking at an insulation life of maybe 2 or 3 years. So this obviously is a significant problem. Now, as we said before, the way that we get past this is obviously doing a good repair process, doing a good burnout process, and monitoring the core losses. So what we do is in our repairs is we do a core loss before we burn out the machine to get a baseline to establish where we are. And then after the burnout process, we'll do it again. And with that, we can then compare and say what happened to the losses in the machine. Has the losses increased significantly? Coupled with that I'm not covering in this presentation is things like hotspots and core heating and things like that that we will look at as well. So what really happens with this big machine, this 43,000 horsepower machine? What really happened, obviously, we followed the correct burnout process and we did monitor the core losses before and after the burnout. We did look at the Stator copper losses. We made sure that we put the correct insulation back. This is not an old machine. It's only 10 years old. So there was no significant opportunity to use better insulation because it was already good insulation because it's not that old. So we could maintain the losses. The final testing of the machine on our test bed, we compared it to the OEM test results, and there was no difference in the performance. We put the curves on top of each other, we superimposed them, and you could see no difference in the performance of the machine. So effectively, what we've done is we've done that first rewind, which should not have occurred for the next 20 years. We've restored the machine back to the original condition. You see on the left-hand side, the guy sitting inside of this Stator. It was quite a job to rewind. It was beautiful coils, really massive machine. It's sitting inside as they insert the coils. The Stator rewinds at Smith Services. Now let's look at our case study too. I promise you I will go a little bit into this. On the right top, you'll see the failure of the machine. It was a design defect. What happened was we frequently see that people, OEMs, try and make the machine as economic, as cheap as possible. They use what's called a underbar design for the rotor winding. What happened, the brazing between the bar and the ring fractured. On the bottom right, that was the proposed design that we offered the customer, that we would use a forged end ring, what's called a sidebar configuration with milled slots for the rotor bars. And the effect is that the strength of this point of failure has increased 5-fold mechanical strength. Now, because this was also an old machine, if I remember correctly, I think it was a Jamont, we have the opportunity to also do a design change on the Stator to put in more copper in the slot, use much better insulation, because this was an old machine. And you can see at the left bottom that the proposed improvement that we could actually improve the efficiency of the machine by 0.4%. Significant improvement. And the nice thing is it's not just during a repair that was needed because the machine failed, but it was also taking that machine and saying, how do I make sure that now I don't just restore the original condition, the original efficiency, but how do I make it better? And again, this is really just applicable or possible in machines that are relatively old, because modern machines, for the most part, use great insulation. They designed well, and we don't see, unless the OEM made a real mistake somewhere in the design or something, we don't often see where a glaring opportunity for improvement. But if we do, we contact the customer and say, we can make this machine better for you, better performance, reduce temperature rise, reduce losses, reduce efficiency, as well as longer life. Now, in conclusion, by investigating what the losses in an electric machine are, how these losses are influenced during different repair operations, and the effect of the changes in the losses in the machine was shown. When the repair process is correctly done and verified through testing, we can repair the machine multiple times without significant effect on the motor's efficiency and performance. Unfortunately, sometimes it's damage that occur, for instance, on a stator core, that will require us to do something to the core. Sometimes it's a restack, sometimes it's a core replacement, which costs more time and more money. But it's important to give the customer that option and say, this is where your machine is, this is the model performance of the machine currently, and this is what will happen to the machine if we repair it as is. Sometimes the repair also offers opportunities to implement upgrades to the machines to reduce losses, increase efficiency and performance, as well as to sometimes rectify design deficiencies or causes of failure in order to achieve long-term reliability, dependability. Thus, in conclusion, when correct repair processes are followed, the medium voltage motor or generator can be repaired while still maintaining motor's original performance and efficiency. And there's a couple of references that you will find in the notes to the different companies that I mentioned, Compound Systems, and my LinkedIn profile and ResearchGate, where you will see this and other papers that I've published. Thank you very much. Tom, back to you.
All right, terrific, Hank. That was a great presentation, and we've got plenty of time for some questions, which actually have been coming in pretty good while you've been giving your presentation, so I think we'll have a lot to talk about. For those of you who do have further questions for Hank, go ahead and put those questions into the Ask a Question box. It's to the left of the main slide window, and we'll get to as many questions as we can in the time we have remaining to us today. Also, any questions that we can't get to on today's live day event, or any questions that come in for those of you listening on demand, those get sent directly to Hank, and he will reply to you one-on-one and get back to you on the questions you're asking. So, Hank, let's go ahead to the first question. I'll go ahead and read these out. The first question involves an end user, and they say, I don't have a high-efficiency motor, but just a standard industrial motor. How does this presentation today apply to my motor?
Yes, thank you. That is an excellent question. The case of it's not just about high efficiency motors. The thing is that we have a motor with losses in it. The losses generate, and obviously the losses. The losses is then energy that I need to supply, which is cost in energy, and the heat is heat that I need to get either out of the building, out of the machine, and it damages the insulation, it ages the insulation. So whether it's a high efficiency or standard efficiency motor, in both cases, I need to make sure that those losses are maintained during the repair. Some cases, if I can reduce them, that's good too, because if I don't, then the machine will not last as long as it should because of the increased temperature, or the machine will cost me more in energy costs. That's why it's important for not just high efficiency motors, but all machines.
Okay, great. We've got a question from an attendee on sensors, and the question is, what are the kind of sensors to be placed in large motors to avoid the failures and for predictive maintenance? I think they're asking about what would you consider to be essential, necessary sensors?
Great. That's a fantastic question. The easiest one is two things. One is the temperature monitoring of the winding and the bearings. That's very important because you want to see at what temperature the motor runs in the windings and the temperature, and you want to monitor that over time. You want to make sure that there's no increase, because what the increase shows you, the losses increase. Now, if the losses in the stator winding increase, when the load is stable, it means something is wrong. Is there maybe a thermal buildup? Maybe there's dust and dirt built up on the insulation that's thermally insulating the winding, which then would increase the insulation, the temperature of the machine, or in a bearing, if temperature the increased losses might mean that the bearing is starting to age. Maybe you need to say, well, I need to pull this machine in order to replace the bearings, or if it's Babbit bearings, to have them redone. The other thing that people do, those are the easiest, the vibration, the temperature and the vibration, to monitor vibration. What people sometimes do is they do like partial discharge measurements. That is really just done on like 10 megawatt and larger machines, because the cost of that is really expensive. And there you are looking at machines that last 20, 30, 40 years. Because partial discharge failures typically is a 20, 30, 40-year event. And you want to monitor that over time in order to prevent the failure. You basically want to, when the insulation is degraded as far as it can go, and then you want to remove the machine before you have a failure, because a failure, if you have this 30 megawatt machine and you had a failure in the slot, it could burn a massive hole in the core, which might cause you to have to replace the entire core, which will cost you a fortune and a lot of. So that is really just done on very large machines.
Okay. It's interesting that you mentioned partial discharge in that context. When Plant Services asks its readers about their predictive maintenance best practices, we get a large group, just short of a majority, but a large group all say that they engage in partial discharge testing. So we've got a lot of fans of that method.
Right.
So, all right, we've got a root cause question, and this person's question is, why does my motor have more noise after rewinding?
Wow, that's a great question. I've seen these. It doesn't happen. It doesn't happen often, but occasionally, what happens is, and I'm not saying where cases when somebody did a bad repair and the bearing is not good and it makes a noise. What you sometimes get is the Stator winding consists obviously of the different coils, and there's connections between the coils. Now, certain combinations of winding designs versus parallel circuits, and I don't want to bore you with all the details, can create an electrical noise when there is a slight unbalance between the different circuits of the winding. Like I say, it happens rarely. You sometimes get it on high pole numbers. The way that you would fix it on the Stator winding, you will actually, it's called balancing or equalizing, where you will make interconnections between different circuits in the winding, and you will fix that. But that really, the repair company should actually pick that up on test already. When they run the machine after the repair, they should have seen that. I mean, it's literally a humming noise. The machine, it will have vibration on the core. You can measure it, and you will hear it, and it's voltage dependent. It happens occasionally, and when it happens, it's not too difficult to process. Even on a machine that's been repaired, you can open the connections, add a couple of wires between the different parallel circuits, equalize it, and boom, the problem is gone. But that's a great question.
Okay, so it doesn't sound like you would ever recommend a rewinding just because of that noise. That there's that more simpler solution. Okay.
No, there's a simple solution to that. Yes.
Okay. Well, we've got a good question on burnouts. Someone was paying close attention to that part of your presentation for sure. This person says, "Hi, I'm a mechanical engineer. Is there any standard or international guideline for performing the burnouts that you mentioned?"
The best place for resources on that would be ESA. ESA is Electric Repairers Association of America, or actually worldwide, and they have a really good standardized manual where they do repair recommendations, because there is no IEEE or NEMA standard that says this is how you should do it. But ESA is really, really good in where they've, over time, they develop systems of how cores should be burned out. They've got a technical service manual that explain how it's done. Some of our workshops are audited by them, where they actually come in and audit our burnout process to see that it's done. But the best place would absolutely be ESA, EASA, Electric Repairers Association, for that.
Excellent. And I'll put a quick commercial in that Plant Services is a proud media partner to ESA. We were at their convention this year, and Hank, I'm still kicking myself for missing you, meeting you one-on-one down there in Fort Worth this year.
Yeah.
But if you look on plantservices.com, I know ESA has shared a number of its articles written by Tom Bishop with the Plant Services audience. So if you're looking for good articles on the content, ESA.com is a great place to go, but also you can check out plantservices.com and look for articles from Tom Bishop. All right. We've got a rewind question, Hank. And here's the question. Is there a limit to the number of times a motor should be rewound? And if so, what's the reason for the limit?
Yeah, that's a good question. If we look at back, I've had this question before from customers. If we look back at our losses, there are different things that we have. We have a frame of the machine that lasts, 100 years, the mechanical frame. We have the core. As long as we test the core before and after each rewind, we can qualify the condition of the core. We can qualify is the lamination material degrading by looking at the losses. And like I've shown in the presentation, we can look and see when are the losses too much that it would influence the repair or the machine performance. Things like the shaft, most shafts has got a design life, which the OEM would be able to give to you, but it's normally decades. So how many times can I repair the machine or rewind the machine? I don't know, 20, 50 times, whatever. As long as you make sure that you do the measurements to qualify the condition, you can repair it as many times as you like. Practically, I've heard of companies that said after 10 rewinds, we should throw it away. 10 rewinds should be a life of 10 times 8, 80 years. So how many plants last 80 years? I mean, so
right.
It's difficult. It's more important to say when we repair the machine, let's make sure our repair company gives us really good reports before I start the rewind and say, give me that core test report that I can actually see what the numbers are, things like that.
Okay. Terrific. This same person has a good time-based maintenance question, and they say, are there regular checks like hourly checks or other similar PM activities that should be made on motors during operation? And how do I determine the frequency and necessity of these checks? I'm guessing some of that information can be drawn from the nameplates in the motors, but yeah, Hank, any advice on PM type activities and regular checks on these motors?
Sure, absolutely. The most machines out there are monitored continuously by temperature and vibration. As I mentioned earlier, have a look at your temperature monitoring. That could be in your SCADA system. Monitor it over time. If there's a significant change and there's no low change, you need to investigate. And that is done continuously, temperature and vibration. Normally, another thing you need to look at machines is greasing or lubrication. That's very, 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 it's very, very important. On the nameplate, it should tell you what is the regreasing interval or the oil life. Do look at that. Do grease the bearings with the correct amount of grease and the correct time frame of the grease. We see often that people send around their routine maintenance stuff and they grease every bearing, what they can find. That is not a good, it's easy, but it's not good because over-greasing is just as harmful as under-greasing. What happens with over-greasing is when there's too much grease inside the bearing enclosure, the temperature of the grease increase, similar to the chemical degradation of the Stator winding insulation, similar is the grease. When the temperature goes up, the grease degrades quicker, and then it will fail quicker. So definitely look at your bearings. Then most OEMs recommend every 4 years that the machine should come out to a repair shop to do a split and polish, clean the winding, check the bearings, stuff like that. And we think it's good to do that just to make sure that you keep the machine mechanically. And then most OEMs, if you read the manual, which we know people don't read the manuals, but if you read the manual, look right at the back, of that GE or that ABB manual, right at the back, it will actually tell you in the manual, every 6 months, every year, you should do all of these kinds of checks. And that's what I could recommend. If a customer's got a question for specific machines, we can look at specific cases of specific machines and do recommendations for each machine. But on this forum, it will just not be possible to cover everything. But thank you for the question.
No, it's a great point about the manuals for sure. And more, I mean, they're accessible online too, so you don't have to wait for the paper copy.
Yeah.
Hank, we've got time for 2, maybe 3 more questions. I think we're moving along just good here. But we can tackle a few more. This question is, oh gosh, this issue came up a lot at the ESA convention. So I'm curious to know what your answer is going to be on this one. With respect to smaller HP motors, is there an HP motor that you think would be considered too small to be worth a rebuild?
Ouch. Hey, I work for a repair company. We repair. No. No. There's definitely 2 different cases. The one is the economic case. The economic case is if you have a standard frame size NEMA motor at 10 horsepower, I can buy it from 500 different suppliers on the internet. That machine will most probably not be economical to repair. If it fails, if I have to do a rewind, say, it will cost X amount of dollars and will take a week. Literally get the motor tomorrow from a distributor. So most likely those type of machines that you're probably looking 50 horsepower and below. It's not going to be economical to repair. We will repair it for you for sure, but it's cost you too much money and too much time. We don't want to waste it. That's the stock standard NEMA motors. Then we have a different class of motor, which is the non-standards. Those are machines with a non-standard frame size, with a special mounting arrangement, with a special shaft extensions, and then nuclear motors that we repair. Those we will repair everyone, irrelevant of how big it is, because the customer cannot get that machine. Either the manufacturer don't exist anymore, or the manufacturer does exist, but they don't build them anymore. Or like in the case of a nuclear machine, it will take the manufacturer a year to build the machine. And in those cases, we do repair the machine. It does cost more than the standard machine, but it's not a standard machine. So that's the best way I would think. But for standard machines, probably 50 and below, it's not going to be economical to do it. Just pick up with your local motor distributor. Do definitely compare the prices on those standard machines because it may not be economical to do.
Okay. No, that's a fair way to look at it. Economic analysis, balance out the costs. Looks like we do have 2 more questions to go today, so this will be the first one. It's a core question. How do you know if the core of an electric motor is bad so as not to rewind on that bad core?
Okay, great. I didn't go into the specifics of core testing, but basically what you do is before you burn out and then after you burn out. So before you burn out, the winding has failed. What you do is you wrap some wire. Now, obviously, these are calculated. It's not just somewhere. You calculate how many turns you put around the core, and you energize the core. So you induce the magnetic field into the core, and then you measure the losses. Then you calculate the core weight, the losses, and then from that you calculate watts per pound loss. And then you do that before and after the burnout. That will then give you a comparison of what was it before the burnout, excuse me, and then after the burnout, and you can compare the 2. That is specifically core losses. And those are actually, they're standards as to what these specific numbers would be. If you get stats 10 watt per pound, it's a bad core, period, because the losses is way too high. It should be probably below 5. Some people say below 6. Some say below 7 watt per pound. The other thing you also look at is 2 different things. One is hotspots. In other words, as you energize the core, you take thermal camera and you scan the core for a 10 degrees increase in temperature in a specific spot. That's called a hotspot. In other words, where there's a local specific damage to the insulation. Now, the core losses might still be low because it's a whole core, but in that spot, because the lamination is damaged, the core gets hot. Now that temperature, you won't see it in the losses of the machine, but the temperature will damage the insulation. And in that spot, you can then have a repeat failure because of the temperature that you want to prevent. So in general, when you have a hotspot, that's something you can fix. You can, open up the laminations, put some insulating paint in there and correct it. The other temperature one is where you have a general core heating. If the entire core is getting hot. Again, you will take a thermal camera, you will measure any increase 10 degrees above body temperature will tell you that core is bad. Now, that's just in brief. Obviously, there's complete studies, and if the customer is interested, I can give him some information of how core testing is done. But that's in brief.
Okay, great. Well, then we'll move to the last question. It's about ultrasound technology. How much can ultrasound testing help with determining things like winding failures and losses? Or in general, how do you integrate into your PDM program for motors?
That's a good question. I've honestly not seen a lot of people use it because ultrasound is looking for ultrasound, obviously.
Mm-hmm.
Which the way I've seen it, people actually use it was on DC motors, where they actually use it to check that the commutation is done correctly in that you don't. But I mean, on a DC motor, you can also see sparking on the brushes. So I didn't find it to be that useful. The other thing that you can try and use ultrasonic testing for things like partial discharge. But again, partial discharge, I can very easily measure from the outside. So I've not seen people use that in general. Occasionally I've seen it here and there, but not a lot of. I don't know if the technology is widely enough accepted. It is available for sure, but I don't think it's been established well enough. There's other testing that you can do much easier. It's got an established in the market that is being used for many years. So maybe the customer has something specific in mind, we can discuss it afterwards.
Okay. Well, this is probably a good place to pause then and go ahead and wrap up the webinar. Hank, we've covered a lot of ground today, and I want to just first say thank you so much for not only the main presentation, but for the wide range of questions you tackled afterwards.
Oh, thank you. It's my pleasure. I love electric motors, you might have noticed. So I appreciate the opportunity. Thank you.
Well, and I'd like to also thank our sponsor for today, Timken Power Systems, and for everyone who's listening today. This webinar has been recorded, and it'll be available shortly for on-demand viewing. You're also encouraged to visit plantservices.com to gain access to even more tools and resources aimed at helping you achieve success. I do want to refer you one last time to the handouts section where the full set of Hank's slides from today's presentation are available for downloading. They'll also be there on demand. There's also a link to an ebook on how to supply and service the drivetrain and a link to a video on Timken Industrial Drivetrain Repair Services. And for those of you who are listening on demand, there's also at least a half dozen more video links to useful content on motors repairs from Timken Power Systems. Did you like this presentation? Let us know your thoughts by answering the brief survey that will pop up on your screen in about 20 seconds. Your candid answers are not only appreciated, they help us to craft future better events. So thanks again to Hank, thanks to Timken Power Systems, and thanks to everyone who attended. Have a great rest of the day.